So this mini lecture is about work done by non-dissipative, aka conservative forces. And so first of all, there's four overview points to be made about conservative forces. First of all, for a conservative force, one can always define a potential energy such that the work done is equal to the initial minus the final potential energy. Secondly, the work done is reversible, which means when you go one way it's positive, and if you go the opposite way it's negative. And so intuitively, what this means is that you can put money in the bank. That would be the positive way, where you're putting money into the bank, energy being money. And if you go the other way, you can take it out. So it's energy is somewhat like money in this respect. You put money in and then bank on being able to get the energy back again. Thirdly, the work done is independent of path, which means this sketch is meant to show that if you went on the green path from point A to point B, to start to end, for a conservative or a non-dissipative force, the same work would be done if you went on the green path or on the red path, or indeed on any path that started here and ended there. And one of the consequences of this is that if your starting point and the ending point are the same, in other words, if you go around in some kind of a loop and then come back to where you started, no work is done. Okay, now just think about an example of a dissipative force. For example, the force of friction, where, for example, no matter which way you go with friction, if you go this way, if you go clockwise, or if you go counterclockwise, you would be doing work. And so clearly you're not going to be doing zero work if you come back to where you started. It's not going to be zero. It's not going to be independent of path. If you go from start point to end point, you're going to do more work if you go on a longer path than if you go on a shorter path. It's not going to be reversible. You can't get work back if you go the opposite direction from friction. You cannot, in fact, represent the frictional force by the difference of two potential functions. Two examples that we'll look at rather closely of non-dissipative conservative forces are gravity, the gravity force, and the spring force. So let's take a quick look at how those two work out. The potential energy function for gravity is mgy, where y is the height above the surface. And so, for example, if you have a mass m at height y1 and you move that same mass m to height y2, and it's acted on by a downward force of gravity, mg equals F grav, then the work done by gravity is going to be clearly minus mg times delta y, minus because the delta y is anti-parallel to the mg, force of gravity. But delta y is y2 minus y1, so minus mg times y2 minus y1 is mg y1 minus mg y2. And here is the UI or U1, if you will, and the UF, the U2, which shows the form of this function here for gravity. Second example, spring. The potential energy for a spring is 1/2 times the spring constant, newtons per meter, times the amount it stretches. And so x is going to be the stretch amount. Actually, it's not just stretch, it can be stretch or compressed. And so let me add that to the chart here. Compression or compression, either one. And so let's look at an example here where we start with a spring um, of spring constant K, um, and it is, let us say, um, in the relaxed position right here. And so that means x is equal to 0. And let's say we stretch the spring. I'm going to erase this m because really m doesn't have anything to do with what we're doing here. Let's stretch the spring a distance x. And so if I stretch the spring a distance x, the force done by the spring, not by me, but by the spring, is in the opposite direction. The spring is going to be opposite to the displacement, and therefore the work done by the spring is, and this is a varying force, and so what we will do, and I'll talk about this in more detail later, is for the force we'll take the average between the starting force. Well, when it was in the relaxed position it has 0 force, plus the force in the fully stretched position, which is kx, so 0 plus kx divided by 2, the negative of that times x, again the negative because these two are anti-parallel. So the work done by the spring is minus 1/2 kx squared. And so looking at this as 1/2 k times 0 squared minus 1/2 k times x squared, again shows that here is the u initial and here's the u final, and the work done by the spring is u initial minus u final.